Hello, everyone. Yes, I'm Emily Culley. I work with Brad Jolliffe, and honestly, Zach's talks and Louise' talk were a great introduction to my talk, so you're already going to be experts. So basically, as we've already learned, there are non-Mare volcanic complexes that have been identified across the moon. In particular, today, I'm focusing on Gruithuisen, which I'll try to demark in blue, and Compton-Belkovich, which I'll note in pink. So as Zach already covered a little bit, remote sensing analyses suggest that these areas are silicic. So just as an example, here's the Diviner CF data for the Gruithuisen domes, and the blue here shows silicate polymerization, suggesting silicic material. And then on your right, we have Compton-Belkovich, thorium data, which also shows this hotspot, if you will, of an enrichment of thorium. So additionally to remote data sets, we can also look at the volcanic morphologies. We can look in the visible range. And so here we're looking at the three domes of the Gruithuisen dome complex, if you will. Today, mostly I'll be focusing on Gamma Dome, but there's also this Northwest Dome and also Delta Dome, and their shapes and slopes are further evidence of extrusive volcanic structures. We can do a similar thing for Compton-Belkovich, and we see here that there's this East Ridge and West Ridge, and then this Alpha Dome, which looks a little bit similar to the Northwest Dome, which it's with its tall or small width to height ratio. And then there's this caldera in the center, or this assumed caldera that collapsed at some point. And here you can see lots of boulders on some of the smaller mounds, and here's a close-up of Alpha Dome. So just like Zach said, the formation mechanisms are not yet fully determined for these sorts of features. It could be basaltic underplating or something like extended fractional crystallization. There are issues with both of these models. For example, we would need a sufficiently large amount of fertile material in order to really confirm a basaltic underplating, and often we struggle with some of the conditions necessary for fractional crystallization. So, wrong button. If we investigate the compositions and the variations in the compositions of these volcanic complexes, then we could help better constrain the potential formation scenarios. So what I do is then a little bit more like what Luis does. And so I look at NAC-derived single scattering albedo, because it's been found both in the Clegg-Watkins 2016 paper and then also in this abstract from Jolliffe et al. 2020, that variations in single scattering albedo reflect variations in composition. And so if we can control the if we can calculate the single scattering albedo, we know something about the composition. So this allows us to investigate the silicic composition and distribution of these domes at the scale of NAC DTMs. And so, for example, here is the DTM for Gruithuisen Gamma Dome, and we can see this primary summit plateau here that we'll be focusing on with some craters and a small peak. And then the Compton-Belkovich map is a little bit more complicated, but just as I pointed out before, we have this Alpha Dome and this sunken collapsed caldera with the ridges. And so I perform an optimization on the HAPKey model using NAC images to calculate single scattering albedo. And then I use the DTMs at that scale to compute the local incidence and emission to try to account for the local topography of the region. So then we can go from a map that looks like this in DTM, and we can find the single scattering albedo. And so as you can see here, single scattering albedo in this case, brighter or more yellow. A higher single scattering albedo means more silicic material. And so we can see that the caldera here is the highest single scattering albedo, the most silicic, and then the ridges are kind of intermediate, and then this material all around is the least silicic in this case. And this figure represents exactly what I just said, where we have the edges of the complex and the feldspathic lowlands, because lower than Compton-Belkovich, but highlands compared to the moon. On the lower end of single scattering albedo, and then the caldera and small mounds on the higher end. We can do the same sort of analysis for Gruithuisen. So here's that DTM model again. And then here is the corresponding single scattering albedo analysis. And actually, it's really interesting. The areas that Zach pointed out were up here and here, which are next to an area that has the highest single scattering albedo for the region, which could suggest the highest silicic content in that region. And so we see kind of a west-east delineation across Gruithuisen Gamma Dome. Here is the simplified scatter chart for Gruithuisen Dome. You can see the highlands and the mare down here with the lowest single scattering albedo, and then the dome crater and central complex with the highest single scattering albedo. So we can now compare them both side by side, and we can see that the values in both regions have single scattering albedos that are indicative of silicic compositions. And particularly that volcanic structures in both regions have single scattering albedos that are higher than those in their surrounding area. So they're more silicic than the compositions that surround them. We can look at Compton-Belkovich specifically and say, okay, so if we assume that the highest single scattering albedo is rhyolitic, then we can mix that with the lowest single scattering albedo, which is this felsic material, to see that the plains and the ridges are probably more of a dacitic composition. And then the alpha dome, which was surprisingly had surprisingly low single scattering albedo, is more 50% silica rich, is more andesitic. Comparing that to Gruithuisen Gamma Dome, we see that the summit plateau contains lower values of values lower than all of the regions in the Compton-Belkovich complex, which suggests that this composition is more andesitic still, or perhaps that there's mixing with some higher FeO source, maybe olivine. In general, these variations may reflect origins from a magma chamber that was undergoing fractionation to get this variation of single scattering albedos, which corresponds to a variation of silicic material. But of course, as my advisor always says, we need to go there. And so we'll be looking forward to the lunar Weiss in situ data that will give us unparalleled insight into the actual compositions and variations within the particularly Gruithuisen Gamma Dome, but hopefully representing what we see in non-Mare silicic volcanic regions as a whole. Thank you very much.
Something else that goes into single scattering albedos grain size. So do you have a way to account or control for potential grain size variations?
Absolutely, that's a great question. So in the calculations that I make, and it's easiest to see in, well, actually in this image here, there are areas where there's no data. And that's because I only consider regions that are mature. And so I don't look at high slope regions or particularly high incidence regions, regions where we may have had mass wasting or more immature material may be shown. As material matures, its grain size becomes more uniform. So although I can't tell you what the grain size might be, I can say that all the grain sizes are approximately the same.
It would be worth seeing if you compare, it's going to be lower resolution, but comparing to like the minor H parameter, which is kind of a proxy.
Absolutely, yeah. I could definitely do that.
I have one more question.
Yeah.
From what I understood, aren't you having like opposite observations to the last speaker regarding that olivine ridge?
Oops, wrong one. Obviously we definitely have to chat more, but on first look, I'm not sure. I think so because one of his circles was here, which has some of that dark color, the blue here, which would be the lower single scattering albedo, and then another one I think was down here. So the trends that I'm seeing could definitely show mixing, particularly because overall, all of the data that I had was maybe lower than I would expect a purely silicic material to be. And so I think there's either more, if you will, pure or less silicic composition in some of those olivine-rich areas, or there's mixing throughout.
Is there a possibility of that to be just like ejecta mixing because these domes are really old and stuff?
It could definitely. One of the other ways that I try to constrain my analysis is not looking at those kind of lower areas or the areas with high slope where we're more likely to have kind of extra ejecta material. So I try to look at the highest topography regions, which is why I focused on the summit of the dome, but absolutely mixing occurs.